5. 1, 3, 1, 1. 1, 3, 2. 1, 2, 1. That's 3 there, so I need 6. Is that do it? 1, 2, 3, 4. Oh, that doesn't do it. So that was the wrong tack to take. So I'm here, I can add 1, lose 1. So 1, 2, 2, 1. So that's, there we go. And there's one more. I think that's it. And then 0, and there's 3 of these. Let's get them nailed down. So 0, 5, 1, and then subtract, that loses 1, that gains 1, that's 4. And then 3, 2, 3, 3. All right. Should be 26 total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. All right, so there's 26 different scenarios here. If we could distinguish between the particles, as I talked about earlier, and just sort of spoiler alert, there's 6 of these. There are 30 of these, 30 of these, 30 of these, 30 of these. And then, because these are in a different order here. So 3, 1, 1. There are 120 of these. Well, and so on. It adds up to 2002. All right. What classical physics says, if I have 9 units of energy and I have 6 particles, these are all the possible scenarios. So I would expect that most likely, if I had to pick a place where a particle is going to be, the plurality of the time it's going to have no energy. Because if I add all of those up, we get 59 total zeros. Out of a possible, well, I've got 26 scenarios here, 6 particles. 26 times 6 is, so out of a possible 156 different places that it can be, 59 of them are at 0. 40 are at 1, energy of 1, 23 here, 14 here, 8, 5, 3, 2, 1, and 1. So on average, if I want to know how many particles are at this level, slightly different, so I'm going to call this sort of N. N would be the number of particles per scenario. Then this would be 59 out of 26 scenarios, and that's 2.2692. So at any particular time, on average, there's 2.2692 particles with no energy. 1.5385 particles with 1 energy, 0.8846, 0.5385, 0.3077, 0.1923, 0.1154, 0.0769, 0.0385, 0.0385. So that's the number of particles on average would be at that energy level if I just randomly picked, I set it up, and then I just randomly took samples, and on average, this is what I would have at any particular moment. So if I took the energy and the average number of particles, and I would like somebody to do this for me, or several people actually. So on average, I'm gonna have that many particles in energy 9, so that times 9, plus, and then that times 8, that times 7, and so on, down to the end, and then what's the total sum? If I multiply the energy level times the number of particles per that energy level.
Is that 0.8846 or 41?
4.6.
You're just looking for the decimal times the, like, 9 and add those up, basically?
Yeah, so the number of particles for that energy level times what the energy at that level is.
And then add all those up.
Yep.
I got 8.8007.
Yeah, what?
8.8007.
I think there's something slightly off of that.
Maybe I typed in a number wrong.
And let me double check, make sure I actually wrote the numbers down.
What is that 30? Is that 3077 or 3033?
3077.
I got the same thing as he did.
Yeah?
Yeah, I put 77, so.
See, 22692, 15385, 8846, 5385.
The 22692 doesn't really matter.
That's 1923, 1154, 769,
Oh.
385, 385.
That's where I messed up, I think. The 19.
Yeah,
I think I put 15. Yeah.
Oh,
yeah.
that's
Yeah, I put 15.
15, how could you?
So it's pretty far back there.
So that would make a difference of, so you get 15, so that's 0.04 times 5, which is 0.2. So that would make a difference of 0.2 here. So you get 9.007.
9.007.
All right.
3
Right.
zeros.
Sorry?
3 zeros.
Now recognize there's some rounding. I only went down to 4 decimal places. And actually, if I took this out to double precision, it should come out to 9 exactly.
She said she got 9.0007.
Yeah.
No, 3 zeros.
No,
Okay,
three zeros.
There we go. Thank you. we have 4 significant figures here and 4 significants there. Oh, we're still off by 1,000. But I hope you realize that's close enough to 9 that we're going to count it as 9. So my total energy, per state, I should say, not my total energy, not 9 times 26. So my energy per state, which I'm just going to represent as a lowercase e here, is the sum of the energy at some particular level times the number of particles for that energy level. Now, if we did the full thing, we would get to this very similar. There are a number of distributions in physics, and just as a side note, what we did right here with these numbers right here, this is known as the Bose-Einstein Distribution. If we actually looked at the number of states here, the fact that this represents not 1 but 30 different combinations, we'll get similar numbers, slightly off, but that's known as the Maxwell-Boltzmann distribution, which is actually the one that we care about more, but I just wanted to get the sense. 2 things: 1, a sense of how you go about it, and 2, this relationship right here. So if I want to know the energy per state, I'm first going to just rewrite what I have over there times n sub I. So the change in energy would be the sum of the energy at some particular state times the change in the number of particles. So if I just looked at a small little, so I think about a distribution and I'm just looking at a small little bit of it. So that would be equal to E sub I times delta N over delta F times delta F. Nothing fancy there, just slowly working my way towards an integral. So dE, now going to the integral, would be the integral of my average energy at some particular frequency times dN dF. This is a very critical equation right here. Because we won't have time today, but we will figure out how many particles there are per state at some particular frequency distribution times the average energy, dF. Now I'm going to spoil some of it. In classical physics, the energy related to particles is just 1/2 kBT times the number of particles. Or sorry, number of degrees of freedom. Well, when I'm looking at light, if I think about light as a particle, light basically has 2 degrees of freedom. In other words, if I have light shading right at you, I can express it in terms of I and J, however you want to do it. I basically have 2 degrees of freedom there. All light can be expressed as some combination of those 2 degrees of freedom. The energy does not depend upon the frequency at all. Energy depends upon the temperature. So my energy per state is going to be equal to my average energy, which is just kBT, because I'm doing a differential with respect to frequency. My distribution, which I'm not deriving right now, I'm just sort of throwing it up here for you, is 8 pi f squared over c cubed, df, from some value to some final frequency. Pull the constants out, so I get kBT, 8 pi over c cubed, integral of f squared df, from no frequency of something really tiny to whatever frequency I want. And this is 1/3 f cubed from 0 to f times this constant out here, which ends up being KVT 8/3 pi c cubed f cubed. So the total energy is dependent upon the frequency cubed. So if I take what's called a black box, and this is not like the black box in airplanes, which are orange, this is literally a black box. You heat it up and you look at the radiation coming out of it. If I looked at the radiation for frequency, according to this, if I looked at the energy coming out for frequency, it would start out small, but as F got bigger, this thing would go shooting off. This is known as ultraviolet catastrophe. We would expect an increasingly large amount of frequency. If this actually were the case, we would have to have evolved differently, or we would have died from the radiation coming from the sun. Because the sun gives off frequency, all sorts of frequencies. We only see within the visible spectrum, but it's giving off all sorts of different frequencies, and those higher frequencies would just kill us, or we evolve differently. From experiments with black body radiation, where again, they take a black box, an empty cavity with a small hole in it so some radiation can escape. They heat it to a specific temperature and they look at the radiation coming out. What it looks like is it drops off. The higher frequencies drop off. This is a huge problem because classical physics predicts this. Experiment shows this. And it's this resolution of trying to fix this that revolutionizes physics. If we make one change in the assumption, we don't assume that the average energy is only proportional to the temperature. If we make the assumption that the average energy is proportional to the frequency, it all changes. And that we'll have to wait for next week.